Functional testing focuses on subjecting the software under test to a set of inputs and verifying the actual outputs match the expected outputs. One of the challenges in functional testing is deciding the input values to test. The software can be in any number of valid or invalid states. Theoretically, each input value can put the software in any of those states. The trick is to identify which values or combination of values or sequence of values puts the application in an invalid state. This can be daunting when the number of possible inputs or combinations of inputs produces a large or even infinite number of inputs we need to consider. The challenge is to reduce the number of actually tested inputs and still have some confidence of the level of quality. Consider testing a simple game such as Angry Birds. With just two variables, angle and force, we still have 2 to the 64 possible combinations. It's impossible to consider all of the possibilities. We need a way to reduce these input values. One way to deal with the combinatorial explosion is to use random testing. That is, pick a random input vector, that is, a set of values for all inputs, and verify the application at those input values. Although this approach effectively deals with bias, defects are typically not randomly distributed throughout the source code. Defects are typically concentrated at the boundaries or logical or numerical edges of numerical values of interest. A better way to deal with the combinatorial explosion of input value candidates is to systematically focus on specific features of interest. The first step is to identify the independently testable features. These are derived from the functional specification, which describe the expected behavior for specific inputs. For instance, consider the inputs to a function that calculates the roots of a quadratic equation. Although the combinations of the inputs a, b, and c can potentially be infinite, there might be some edge cases we would focus on based on the algorithm used to calculate the roots. This would need familiarity with the various algorithms used. In a multifunctional calculator, each function would become an independent testable feature. Instead of considering the infinite set of possible inputs, we want to identify values that are especially interesting. To do this, we use equivalence classes to identify edges or boundaries, values that represent a whole family of values that would equally put the software in a valid or invalid state. Equivalence classes are derived from specific input conditions mentioned in the requirement specification. For each equivalence class, we choose input values that cause invalid and valid outputs. Depending on the type of the input, we consider different various equivalence classes. For input values taken from a range of values, we consider one valid value and two invalid, one right above and one right below, the threshold between valid and invalid. As mentioned earlier, defects are sparsely distributed throughout the product and are difficult to find. As we write code, developers tend to make mistakes misunderstanding the boundaries of values. For instance, when implementing a loop, we might iterate one too many times or one too few times. Or we might mistakenly confuse a greater than from a greater than or equal. To improve our chances of finding them, we can focus on testing these edge cases. Consider testing zip codes, that is, the representation, storage, logic regarding zip codes. Here's a list of concerns regarding zip codes. We need to consider all sorts of possibilities, that the zip code is empty, with many cities as output, 1 through 4 characters or 6 characters, 6 being a boundary value, or maybe not having any non-character data, or maybe having no digits.